I ran across people.
Well, also,
Diehl? Yep, Diehl's right. Is this good for me standing here, or can people?
You can stand here, or like basically, yeah. It's a little bit awkward because of the
cable. Yeah, it's probably fine. Okay.
Hello, everyone. Welcome to the last New York City Systems Meetup of the year. Thank you so much for coming. And we have two wonderful and excellent talks here for today. But before we get started, I want to give a massive thank you to Prelude, our host here for the last 2 years. Dan won't be talking about job opportunities, but he would like someone from Prelude to come up here and talk about opportunities that you currently have. Oh. I don't know what's going on. Josh has to. There we go. Yep.
We're hiring a machine learning research fellow. So if you, security research fellow. So if you're into machine learning security research, come talk to me.
Wonderful. Give me a round of applause, Prelude. Yes.
I work for East River Source Control, and we're working on version control stuff, and we're looking for someone to start working on distributed storage infrastructure.
Wonderful. Please talk to him after the meetup. Oh, another one.
Josh Ross from iGroup. This is my co-founder Jake. We are doing cybersecurity for industrial systems, industrial control systems, PLCs, things like that. If you like messing around with low-level hardware and things like that, come find me. We're looking for founding engineers right now.
All right.
Hey, my name's Jack. I'm from Arch.co. We do automation for alternative investments, and we're looking for a senior infrastructure engineer to kind of like help our engineers with all their tooling, pipelines, and all that type of stuff. So please come see me if you're interested.
Wonderful, wonderful. For anyone who's been here from the first New York City system, this is a remarkable improvement from the time when we opened it up. So thank you for everyone who has open opportunities, and then please talk to everyone after the first talks. Anyway, we're about to get started. Our first speaker is Larry Diehl. He's the founder and CEO of Colimit. He started his career as a software engineer, getting fed up with dealing with bugs and PagerDuty. Today, he's working on developer tooling and AI assistance to help devs with no formal verification experiences with this talk, turning Dafny sets into sequences. Everyone give it up for Larry.
Thank you. So out of curiosity, for some background information, raise your hand if you've at least ever heard of TLA Plus before. Okay. And then what about Lean, the Lean theorem prover? Okay. And then what about, at least prior to the talk announcement, Dafny? Okay, cool. Good. So this talk is going to be given sort of like a story in chapters. So at the start, in the prelude, we're going to kind of introduce the main character, Dafny, and how Dafny sits relative to other verification tools. And then we are going to move into Paradise, where everything just works automatically. You write your programs, they automatically get verified. You don't have to do any work, and it is great. And then we will hit the reckoning, where all of a sudden we run into some problem that we, seems like it should be easy, but we don't know how to solve. So we kind of have to go on to this learning journey of the deeper concepts behind Dafny. And then we'll hit our redemption arc and figure out how to put everything that we learned together and solve the original problem. And then finally, we'll kind of review, and then maybe I'll see some of you later at the pub. Also, fun note, I had to, this is based off Markdown, and Markdown couldn't start a ordered list with 0, so I had to do an unordered list. Okay, so the prelude. So this is kind of a rough outline of kind of major categories of formal methods tools. So we have, on the one hand, TLA plus, maybe the most well-known of these. It's what's called a bounded model checker, which means you generally represent your, you create a model of a system, like a distributed system or like a protocol, and as a state machine, and then sort of up to some, with some finite set of inputs, you kind of do this bounded enumeration until you reach a fixed point and check a bunch of properties. The nice thing about TLA plus is it's fully automatic. You don't have to sort of write proofs yourself. And then in comparison, something like Dafny is, instead of about like modeling high-level systems and verifying them, it's more about implementing low-level algorithms, right? So if you're writing some sort of encryption library, or maybe like an efficient like streaming library that was like windowing things, then that's something that you wouldn't use TLA plus for, but you could use Dafny for and prove that it's actually correct. And the nice thing about Dafny is that you can actually compile to existing programming languages and ship those, right? So you can compile to like Go or Rust, or to a limited degree even C++, and also Python and JavaScript and Java and a bunch of them, right? And the nice thing about Dafny is also that at least the proof part is sort of semi-automatic, in that it uses a field called automated theorem proving, where you generally only set up the specifications of what, that say how your software should be correct, and then the tool will handle writing the proofs, or at least when you write your programs, it'll handle checking to see if your programs conform to the specification, with you needing to do, let's say, minimal work. So I wrote like semi-automatic because sometimes you have to do some amount of work to kind of coax it in the right direction. And then something like Lean, for comparison, it's called an interactive theorem prover because the work is interactive or manual, like you do all the work. It has a more expressive type theory. It's higher order rather than first order. So in general, you can express more things more easily, but at the cost of you have to do all the work yourself. Generally, it's used in math and type theory, kind of more academic disciplines, rather than necessarily for kind of applied, like writing software. I'm sure everybody from these communities would kind of get angry about different parts of the way I'm simplifying this. But one noticeable thing that'll come up with Dafny is it uses something called Floyd-Horde logic, which is sounds more complicated than it is. It just means when you have a program, the correctness of that program is stated in terms of preconditions and postconditions, or things that should be true before you execute a statement and things that should be true after you execute a statement. And we'll see some of that today. And yeah, I think that's enough on Dafny. So now we're going to enter Paradise. All right, so we're going to create a model of a bank account here. And one nice thing, as you can tell from Dafny here, is that the syntax looks like a conventional programming language, right? So we have like data types. This is a record here. In general, it could be an algebraic data type. And then we have some classes, some mutable variables. And so here the bank contains a sort of like instance variable, if you will, of a map from IDs to accounts. And the accounts have, importantly, some balance associated with them. And then this predicate is what we will use. So a predicate sounds more complicated than it is. It's really just a function that returns a Boolean. So the valid predicate will be what we're using as our sort of invariant. So if you're familiar with stuff like TLA+, this is kind of what we'll be using for invariance. And then the change balance method, if we kind of focus on that a little bit, will have some parts that look familiar, like it has a type signature of kind of input and output types. It has some parts that look a little bit not so familiar, like we're actually kind of giving a label to our result type. That's not something that you typically see in a type signature. And then when I said before, we state specifications or correctness in terms of preconditions and postconditions. Requires here is our keyword for preconditions, and then ensures is their keyword for postconditions. So in general, we could kind of have more complex preconditions, like we could say requires the integer should be positive, for example. And then we could also have more complex postconditions, like we could kind of state things about what our result should be when we kind of execute this program, this method. And another kind of unusual thing is we are explicit about when we are using imperative features. So this is saying this method can modify this class because it might change, the map of accounts. And yeah, that's kind of a beautiful part about Dafny is you can tell all the sort of capabilities or effects of what this method can do based on the kind of type signature, if you will. And yeah, so basically what's going to happen here is we're going to start filling in these definitions so that we are going to maintain this validity invariant. So this, whenever we call this method, valid needs to be true, and that's something that's going to be statically checked, right? So if we ever kind of write a program where we try to call change balance and the invariant that we're for valid is not true, we're going to get a type error or like a static error. And then as a reward for maintaining that kind of static discipline, we're kind of guaranteed that our invariant is maintained afterwards. Okay, so here's the definition of valid. It has this maybe somewhat scary looking for all keyword, but for the purposes here, this is really, you can think of this as just like a for loop or iteration. So kind of for all IDs in the accounts of this map, we want to assert that the, for example, the balance should be positive and the email should not be empty. And another kind of interesting thing is the ID, the key of the map should equal the ID that's actually in the object on there, right? So this is going to be kind of the invariant that we're trying to maintain. And yeah, I mentioned before, predicates are just kind of syntax sugar for functions returning Boolean, so there's really nothing scary there. And then the definition of change balance, so if you kind of ignore the parts of the type signature that are maybe less common, then it reads just like a program that you would write directly, which is, I think this is kind of the most amazing thing about Dafny is you can write programs like normal and get verification. And if you kind of are, disciplined about staying in the fragment that it's good at, then you kind of have to do no additional work, right? So here we're going to say, okay, if the ID is not in accounts, the ID that we're trying to change the balance of will return an error, and then we'll grab the old account. Notice that we're actually doing things like indexing by ID, and if we had an out of index error, we would actually get a static like compile time error, and that is not happening because we're checking that the ID is in accounts beforehand. So there's some like sophisticated stuff happening behind the scenes here. I mentioned in the earlier slide, Dafny on the verification side is powered by SMT solvers, most popular of which is something like Z3. But basically what happens is a bunch of constraints are generated. So when you try to do this accounts map lookup, then it will create a constraint to this mathematical tool, this sort of SMT solver called Z3, and then the fact that we sort of ahead of time checked this condition will sort of discharge that constraint later. So if we remove this and then we try to write that, we get a compile time error. And then, okay, now we're going to compute the new balance, take the old balance, add the amount. Then we'll check that the new balance is actually, we didn't go negative, we don't owe anything in our bank. And then we will update our existing account with the new balance. And then we will update our accounts map. So this kind of second to last statement is the imperative part where we're actually mutating some state, right? And then finally return the new balance. So the interesting thing is if we look at the validity predicate and the change balance code, excuse me, the code that I've highlighted here is kind of showing the points that are going to be statically checked. So if I remove any of these highlighted lines on the left, I will get compile time errors, and because I would be breaking the validity invariant in the kind of post condition of this method. And so this is like a pretty incredible slide, right? Like it looks like we're just doing ordinary programming and we're getting this like incredibly powerful kind of static checking and like absolutely no effort, right? So now there's one other thing that where there could be a problem, and that problem, does anybody have a guess at like something that we in the previous code here, if we sort of did it wrong, we would not statically catch a bug?
Concurrency.
Concurrency? Oh, that's a good point. So concurrency is not handled by Dafny, so that's one of its downfalls. Yeah. Yep.
Yeah, I guess when you're checking if ID is in accounts, if you're not ensuring that it's a precondition and you forget to do it in your implementation, there could be an issue there.
So we are checking IDs in accounts here, so that part should be good. So it's a little bit subtle, so let me just kind of move to it. And the answer is we're returning this result with this balance, right? But the only thing our post condition, our valid, our invariant is ensuring is that we never get negative account balance in the state. But it's kind of actually more interesting. We can kind of add another post condition that says whenever our updates are successful, then the value that we return from the result should be equal to the lookup in the new account state and its balance, right? So where we could have previously had a bug is we could have returned OK from old account.balance and everything would have statically compiled. But if we kind of add this extra post condition, and here's maybe a nice demonstration of the dependency on the result type being used, right? So then once we add this extra post condition, now we have that extra static guarantee that we can't create bugs like that. Okay, so this was great. And now we're gonna, so there's this famous paper, Why Functional Programming Matters. There's a little bit of a pun here. Now in that paper they talk about some things like, oh, functional programming is useful because you have a good concurrency story, you can sort of reason about the programs nicely, they're kind of, has a good modularity story. But I think there's one kind of undersold benefit of functional programming that is very apparent within Dafny, and that is code written as pure functions can be reused, so sort of program reuse, in the specification world and in the implementation world. And as a concrete demonstration, let's try modifying our previous program. And what we're going to do is, instead of explicitly checking that the balance should be positive from the variables we built up, we're going to do something kind of weird where we're just going to go ahead and optimistically update our accounts state with the new account, and then we're just going to check is everything valid after the fact, and then if it's not valid, we'll sort of like abort our transaction and reset the accounts back to the old accounts. And this seems like incredibly dangerous normally, but because everything is being verified, we kind of, we can lean on all that extra safety that we have. And the nice thing here, the thing I'm trying to point out, is that this validity function is being used both in the specification context and in the implementation context, right? So in Dafny, as a rule of thumb, I think it shows why functional programming is so nice, is that you can use it across those contexts, whereas like a purely imperative program you can't use in a specification context, because Z3, the constraint solver of SMT that's doing the SMT solving, requires kind of mathematical objects to be able to do its reasoning over, and imperative, non-terminating programs are not mathematical. Okay. So now we're going to get into this problem. So everything seemed great so far, right? So the problem is going to be, okay, let's say I want to write a function that takes a Dafny set and returns a Dafny sequence. I'll also use the word list a lot instead of sequence in this talk. They're the same. And now the problem is, like, let's say I was in a programming language like a functional one, like Haskell or OCaml or something like that, then usually if I had some sort of set-based data structure, maybe underneath the hood it would be some sort of balanced tree, and that would be maintaining some order, and we could sort of recurse over that tree, return a list, and be done with it, right? But the odd thing here is, in order to get all of this beautiful kind of proof automation and verification for free, Dafny identifies data structures like sets and sequences and maps with their kind of primitive logical mathematical definitions in the SMT solving world. And in the SMT solving world, the mathematical definition of a set does not have a notion of order, right? Sets are unordered. So I'm kind of like left in a pickle. Like, I have this unordered set and I want to produce this list, and this list has a particular order, and there's no primitives in the language like to kind of list this thing. So what do I do? And that's our big problem, right? So we're going to kind of introduce ourselves to like a little zoo of languages. In Dafny, there's executable sublanguages, and we've already seen some of them. So predicates and functions are these, purely relational or purely functional things that we can use both to write specifications and to write implementations. That was the nice benefit that I pointed out. Whereas methods are mainly used to write kind of usually optimized implementations. They can be procedural, right? So you can have like early returns, kind of jumps, and this kind of thing. They can be imperative, so they can mutate state. They can be non-terminating, so we can like write servers that never, that keep serving requests. And they can be maybe a little bit unusually non-deterministic, so we can do things like flip coins, and and that non-determinism will end up being very important in this talk. Now, the other side of Dafny is the non-executable part of the language. So there's this keyword called ghost, and it's kind of a modifier on top of predicates and functions and methods. And if you put ghost in front of something, it means that I'm not going to compile code for this. So I'm strictly using it for verification purposes. Actually, if you use the VS Code mode in Dafny, it's pretty nice, because the ghost, anything that is in ghost mode will turn transparent, kind of like a ghost. Ghost predicates and functions can be used to write specifications, and we'll see that they are more kind of declarative or logical than kind of functional or relational. And then ghost methods can be used to write proofs, and they can be both logical as well as like tactical. In the theorem proving world, there's this thing called tactics. And then they can also be imperative. There's also something called lemmas, which are sort of like ghost methods, but ghost methods that don't update state, right? So kind of like pure proofs. And then, so let's take a look at these, at where these differences matter. So at the top, we're going to have this specification for given an integer and a list of integers, is the integer that we have the midpoint of the sequence of the list, right? So in this case, the midpoint should be 3, right? And the way that we're going to specify that is very nicely. We're going to say there should exist some list x is 1 and x is 2, such that my original list is equal to appending x is 1 with the element I'm looking for and appending x is 2. So we can very kind of declaratively state x is the midpoint of this list, and then we can also say that the length of the other two lists are the same, right? So like if this was 1, 2, 3, 4, there wouldn't be a midpoint, right? So then so the reason why we can do this with these existential kind kind of constructs is because we're in this ghost world. And if we drop the ghost modifier, then now existentials will only work if they are bounded, right? So dropping the ghost modifier means that we intend to compile and execute this code. So basically what's going to happen is if you bound the quantification, Dafny can just compile this into a loop that like looks over all the elements, right? Like from 0 to the end of the list, and like looks up stuff and runs this regular predicate. Now the problem is we kind of have to rewrite our predicate to not be as nice or declarative. So we're going to say like, okay, X should be the list lookup, and then the length of the list should be this expression like 2 times the index plus 1. Now, this is not an incredibly complicated program, so you could probably look at this and say, like, yeah, I know what it means. But, you can still kind of make mistakes. Like, what if you forget the +1, or you change this from less than or equals to just less than? So the nice thing is we can actually, like, prove that those things are equivalent. So I won't kind of bore people with, like, looking at the actual proof, but you can at least see the correctness specification that says the computed non-ghost midpoint should be equal to the ghost midpoint, the nicer specification. And yeah, here you can see some of the ugliness of Dafny coming through when proofs aren't automatically for free. You start to have to give it some kind of hints. The nice thing though is those hints are usually just kind of making conditional statements and then doing assertions. So a lot of people are familiar with kind of adding assertions in their code just to make sure that things don't break at runtime. In Dafny, again, one of the features that makes it sort of familiar to programmers is you can write assertions, and those assertions will reflect kind of like extra logical equations at sort of compile time or verification time that the constraint solver can then depend on after it's proven those true, right? Okay, so we're going to play this same trick twice. We're going to also define has midpoint where it's not parameterized by the index. And we can say like, oh, there exists some x, it's some integer, I don't know anything about it, and that works in the ghost world. And then in the regular predicate world, we have to bound that integer by the length of the list, right? So the same thing, we can do the same kind of proof. And the nice thing is, this is a kind of another aside, proofs are compositional. So when we have this correctness proof about has midpoint versus had midpoint spec, we can reuse the previous thing that we proved about is midpoint, right? And this is something that is really powerful and doesn't really exist in the world of testing. So normally you have a bunch of unit tests. It doesn't really make sense to reuse a test. But one of the beautiful things about proofs is that they do compose. So you can sort of like reuse your tests to build more complicated tests, or kind of like write a bunch of proofs about some subsystems and then write a higher level proof about your higher level system that's using those subsystems. And that I think is a concept that deserves to be more well known. Okay, now there's this other special thing in Dafny called var such that, and var such that. So here we're going to write find midpoint. So we have a sequence. We're going to return an option integer if we find a midpoint. In the conditional, we're going to say, well, does a midpoint exist? And again, we can do that in an unbounded manner because this is a ghost function. And then if it does, then we're going to sort of say, well, suppose there was a variable such that it satisfies the midpoint spec, then return it. This kind of seems kind of crazy because we're not specifying how to compute this thing, but that's okay because we're in the ghost context. So this is only for specification. The only thing that the requirement that we have in the ghost context to be able to use this kind of var such that to kind of make things up, make data up subject to certain conditions, is that Dafny has to be able to prove that some value exists for that, okay? And then correspondingly, in the functional version, we can write basically the same thing, except in the var such that, what we're going to do is have the requirement that not only should there be variables that exist that satisfy the condition, but it needs to be unique existence. And the reason why it needs to be unique existence is because we're running a function. Functions need to be deterministic. If they weren't uniquely existing, then they would be non-deterministic functions. Okay? But the kind of crazy thing is if you kind of look at this code, if you would have written it, this is using some pretty advanced expressive features of Dafny to write functional programs that don't exist in any major programming language, right? We're kind of just saying like, oh, we have this sequence, well, if it has a midpoint, then just make up some value such that this other predicate is true, and then return it. And we're not saying like how to find it, but because Dafny can prove the uniqueness of this statement, it will be able to, because it has a sophisticated compiler, write a program that finds that element in the list for you. So that is something that's kind of really cool. This pattern is actually so common that there's a sugar for it. So instead of just saying like if exists and then a kind of var x such that, you can just say you have this kind of binding if statement where you say, well, if there is an x such that midpoint spec passes, then return it, and it kind of desugars to the exists plus the var x above. Now we're going to try to redeem ourselves. Okay, so this is what we're doing. We need to return a sequence based on this set that we have, and we have no primitive notions of interacting with this set. How do we do it? We're going to take everything that we learned to figure out how to do this thing. I apologize ahead of time. This is kind of complicated, but the slides will be available if you want to review it after the fact. So the first thing what we're going to do is write this set to sequence ghost function. This is going to use familiar things. So we have this set, it's going to return a result, and we also have this nice correctness specification that says the sequence that we return, if we take our set and turn it into a multi-set, or a set that is allowed to have repeating elements, and we do the same for the list, then these are going to be equal, right? So this is basically says like we're not just like making up elements, like we're really going to get the same things. So we're going to say if our set is empty, return the empty list, else, well, give me an x such that that x is in my original set, and then we'll take that and then append the rest and recursively call ourselves with that element removed from our input set. So this is another kind of like crazy function because it's in the ghost world, so it can use these kind of like crazy, beautiful declarative mechanisms to write things. And then let's say now we're going to do set to seek method. Now methods, remember, can execute, and here's where non-determinism from Dafny comes into play. So what we're going to do is we're going to say, okay, take our input set, set remaining equal to our input, and then we're going to do this while loop where we grab a random element in remaining. So now we're using var such that, which when executed in a method context will non-deterministically create a value that satisfies this, right? So it'll basically, from some element in the set, it'll pick one at random, and then we will kind of accumulate those at random and build up a sequence that way. So that is that. And then the next part will be, we're going to define this function called set to seek sorted ghost. I apologize for the naming here, but so set to seek sorted ghost is going to say, it's going to take some sort of comparison operation, this less than or equal as a parameter. And what it's going to say is not only do we not lose any elements, so our multi-sets are equal in the post condition, but we're actually going to say that the resulting sequence is sorted by the less than or equal function we're passing in. And this will again be originally in the ghost context. We're going to kind of use this as a lemma to write the ultimate set to sequence that we're trying to do. But you can sort of start to see where we're going with this. Like if we have this unsorted list, and we want to create a kind of a list that has a particular order, we need to do that somehow. Well, it turns out we're going to be sorting it, right? So the idea is we're going to call set to seek ghost, get back our unsorted list, and then we'll use the Dafny standard library, just merge sort by, and then we will get a function that satisfies that. The type signatures of the kind of helper methods are transparent here if you want to look at them more closely later. And at this point, you might feel like this, right? So we're trying to turn Dafny sets into sequences. We have all this machinery built up, but the good news is we're at the last step. So we're going to introduce one new concept because there hasn't been enough yet today, and this is something called function by method. And function by method is this really beautiful thing in Dafny. So we're going to define a function called set to seek sorted. It'll be non-ghost. Now, the mathematical or the specificational definition will be the set to seek sorted ghost that we previously defined. Okay, but we need to be able to compute this at runtime. So at runtime, we're going to define a method, and then Dafny is going to prove that both of these things satisfy the same specification that we're giving. So it's going to prove that set to seek sorted ghost gives us a kind of multi-set preservation and the sortedness property that all elements next to each other are less than or equal. For the ghost side, and then also for the method side, how does the method side work? Well, we call our previous function that'll give us, like randomly, non-deterministically kind of give us a list that was ordered based on choosing elements from the set. Then we will merge it, and then this last sort of unique thing is underneath the hood, it's doing some more of that assertions that I was talking about, so that Dafny can actually prove what we're trying to prove here, and then finally return the result. And that sort of does the trick. And again, the beautiful thing is we have this kind of efficient implementation at runtime that, it's using a while loop. It doesn't consume the stack. It kind of has interesting average time behavior because it's randomly selecting elements like in a non-deterministic way. And then we have this other beautiful specificational definition when we're writing our proofs. Okay, so now we get to the postlude. What we learned here is that Dafny is sort of the perfect blend of code and free verification, caveat when it works, right? And one of the costs is that the automatic theorem proving primitives are those that exist in SMT. So we sometimes need to do workarounds to kind of bridge those two worlds, as we've seen today. I promise if you kind of do a Dafny tutorial, it's not going to get this advanced. I just kind of wanted to show, if you kept at it, you're going to run into these issues, and hopefully you can kind of look back on this and resolve some confusion if you need to. And then beneath the surface, there's a wild zoo of these sub-languages, different trade-offs in terms of expressivity versus can you run it and all these things. Can you reuse it between contexts or not? Is it efficient? And then you can use, luckily, advanced and expressive features to help pay that cost of having the SMT solver back all this stuff. Now, the last thing I will say before questions is, so the startup I run, Colimit, what we are trying to do is sort of help people that are programmers that would be interested in learning, like, how do you build formally verified applications? So we're building something called Colimit Code. It's a coding agent that helps you build formal specifications and models of, when I say models, I don't mean AI models, I mean the real models, the mathematical models, and models of your applications, and then prove that those kind of state machine models satisfy your logical specifications statically. Also use kind of hybrid of traditional compilers for code generation, and only use LLMs where you really need to, so kind of restrict them a lot. And then, in places where you can't statically verify, do things like model-based testing or property-based testing. And I think this kind of underscores an important point. A lot of people sort of think that with LLMs, kind of the world is ending. It produces all this slop. It's kind of making everything sort of annoying. And one perspective might be, oh, we should use better tools like maybe formal verification to kind of correct you from that slop. I'm not saying that's wrong, but I think a more interesting positive spin is to think about the fact that LLMs have allowed non-technical users to start learning to program. And with Colimit Code, what we're trying to do is to help programmers that don't have kind of formal verification experience learn how to write verified code. Right? And I made this special email, nycsystems@colimit.ai. If anyone's interested in sort of early access, yeah, happy to get you in. That's it.
Are you required to write the ghost? Like, there are these two, is ghost like the signatures in Haskell, and you have to have both the ghost and the implementation thing? Otherwise, why do you have ghost at all? Like, why do you have the two of them?
Oh, good question. So the question was, are you required to have these ghost functions or not, right? And I think if you were playing in the functional world, then the answer is you're not required. And that was kind of one of the benefits that I tried to spell out, is in the functional world, you can use your purely functional definitions both as specifications and as implementations, right? Whereas in the method world, you sort of rely on some sort of specification that's more mathematical. However, kind of as we started to see in some of that like is midpoint code, sometimes even the functional versions aren't completely clear, right? So, one argument is like, well, it's a pure function, your code is your specification. Well, sometimes even purely functional programs can be complicated to understand. And if you kind of go up to the logical world, the more declarative world, where like you have like unbounded existentials and you can have var such that only needs to exist but not uniquely, you can have more terse specifications. So the answer is no, you don't need to have ghost functions, but they can make your specs easier to understand. Yeah, good question though.
Can you explain the purpose of the multiset? So within your specification, like in the function definition, let's say, you have like multiset xs equals result, multiset result. You said a multiset is a set with repeating values, which sounds like a sequence or a list. So why do you have this?
Yeah, so the answer, that's a really good, let me repeat it. That's a really good question. So the question was, why was I using multi-sets in the kind of post conditions instead of like just sets, right? Like I already have a set. Well, one of the answers is kind of like in the title of the talk, which is I can't create a set. I can't turn a list or a sequence into a set. Right? That doesn't exist as a primitive, but multiset, like list to multiset, is a primitive, right? Because in a multiset, because basically in an arbitrary list, it can be like 1, 1, 2, right? If you try to two-set that, there's like a discrepancy, but if you multiset it, then you can kind of preserve all the information.
So what I'm asking is why not turn that set into a sequence, like 1, 1, 2 equals 1, 1, 2?
So there's basically, there's no built-in mechanism in something like Dafny to turn the sequence into a set, right? Yeah. And as we saw, there's a reason for that, and it's because you'd have to kind of choose the sorting order, right? Like there's many possible interpretations, many possible ways you could do it. Whereas with a multiset, there's a unique interpretation. Yeah, but that's a good question. Yeah, thanks. Mm-hmm.
I think you mentioned Dafny compiles to various other languages, is that right?
Yes. Mm-hmm.
So yeah, I got me wondering, how, given that other languages have many different ways, like in JavaScript, an int is actually a float. In other languages, an int is, you have to say what size it is. How does the compiled code deal with those sort of problems?
Yeah. So the question was, Dafny compiles to other languages. Other languages might have certain primitives like integers versus floats. Maybe some are unbounded integers, maybe some are not. So Dafny, when in its compiler, if there aren't sort of immediate matches, it'll kind of create sort of abstractions that it compiles to instead. So an example is the maps in Dafny are immutable maps, right? That doesn't exist in every single language. So Dafny sort of has like a library per compilation target that defines what an immutable map is, and then we'll compile it that way. Similar things with the other data types. Mm-hmm. Yep.
So SMT, it is NPR in the worst case or something. So do you ever find that proof generation or satisfiability checking just like suddenly takes forever for no reason, and like how do you navigate handling, like suddenly your compilation takes forever?
Yeah, so the question is, SMT solving in general is undecidable, so it can just take really long. One of the problems with SMT is because it's undecidable, you're not always going to get a this is true or this is not answer. Sometimes it just times out and says unknown, right? So what do you do if things take too long when they're trying to verify? The answer is like you try to, just like with code, you try to not have a monolithic definition. You try to break it up into pieces, and then by breaking it up into pieces, it makes it easier for the verifier. Yeah, so that's kind of what you also do with Dafny. Also, I guess, whether I like it or not, I have an AI startup now, so part of the answer is LLMs can do that for you. Yeah. Yeah.
Have you done any work in the past to ensure that Dafny's symbolic semantics coincides with the concrete semantics of the generated code and things like this?
So was the question, when you're compiling, how do you make sure that the semantics is preserved between Dafny and your target? Is that the question?
Yeah, so if you, in creating a symbolic semantics for a language, you're basically like kind of re-implementing the semantics of the language, but just project into it to Z3, right? And so has there been any work to sort of prove that the symbolic semantics coincides with the concrete semantics?
Yeah, so
verifying Dafny itself, I guess.
Yeah, so I think there's two interesting questions there. One is, does the sort of symbolic world of Dafny map up to its execution world? How do you prove that? And the next is, even in the execution world, per compiler backend, are you preserving the semantics of Dafny per compiler backend? Yeah, I'm not aware of work on either of those. I would imagine the first one is more likely that somebody would have handled, because probably a PhD student is not going to try to prove that your Python backend is correct, but maybe the first might have some work, but I'm not aware. Thanks.
We're going to take a 6-minute break, and then we'll be back.